Let's try an example of approximating area under a curve. So example 5.4 asks us to approximate the area twice, once using the left endpoint approximation and then a second time using the right endpoint approximation. And our goal is to approximate the area under the curve f of x equals x squared over the interval where x gets to go from 0 to 2, and we're specifically told to use n equals 4 for each of these approximations. So let's break down what that means. First off, the interval that we need to divide up goes from 0 to 2. These are x values. So let's go ahead and represent the interval 0 to 2 on the x-axis. And we're using n equals 4, which tells us that we need to make 4 subintervals. So from 0 to 2, I need to break this up into 4 separate parts. So there's the first one, the second one, the third one, the fourth one. And more than just cutting these up visually, I need to know what the x values are that separate each one of these intervals, because we're going to use those to create our areas, if you remember from the last video. So we need to figure out how far apart these are. Remember that we're calling those delta x. And we're going to make sure that we use the same delta x for each one of these divisions. We don't want our partition to have separate delta x's, although that is something that can be done. That's not what we're doing here. So to calculate this delta x, what we're going to need to do is start with dividing our interval into 4 regions. Our interval goes from 0 to 2. To figure out how long this interval is from 0 to 2, you would just take the larger number, subtract the smaller number, so 2 minus 0. So that's the length of our interval, and then we're going to divide it by the number of partitions we want, 4. So our delta x turns out to be 2 over 4, or 1/2. So from 0 to 2, if we would like to have 4 subintervals, each one is going to be like a half unit tick mark. So if we wanted to, we can clean up our picture. We can say from 0 to 2, we'd go from 0 to 1/2, to 1, to 1 and 1/2, to 2. Those are our 4 subintervals. The shortcut or the formula for this, no matter what your interval is or how many divisions you want, you would do b, which is the right end of your interval, minus a, which is the left end of your interval. So b minus a for your numerator, basically just calculating how long that interval is, and then divide by n. That will give you the width of the intervals. From here, we need to define the left or right endpoints. So if we're starting with the left endpoints, 0 is our x sub 1, 1/2 is our x sub 2, 1 is our x sub 3, 1 and 1/2 is our x sub 4, and then 2, that's not a left endpoint. So 2 is not going to get one of these special x subscript notations. Because remember, we're going to use the left endpoint to create the height of our rectangles. So we're going to take each of these x subscript values, plug them into our function. So we need to calculate f at 0, or rather, let's do the general form, f at x sub 1, f at x sub 2, f at x sub 3, f at x sub 4. So our function is x squared. If I do f at x sub 1, that looks like 0 squared, which is just 0. f at x sub 2, that would look like 1/2 squared, which becomes 1/4. F at x sub 3 looks like 1 squared, which is just 1. And then f at x sub 4, instead of writing 1 and 1/2, let's go ahead and change that to be 3/2. They're equivalent, but 3/2 is easier to square. So 3/2 squared, that's going to become 9/4. These are the function values, so we can use those to draw our rectangles. We're going to have a left endpoint rectangle for the first interval with a height of 0. So that one's kind of boring, but that's the rectangle. And then for the second interval, we're going to have a rectangle with a height of 1/4. So that height right there is defined by the left endpoint. For the third interval, we're going to have a rectangle with a height of 1. And again, that function value is defined by the left endpoint there, or rather the left endpoint is defined by the function value. And then for our last interval, we have 9/4, which is a little more than 2. It's like 2 1/4, so got to draw it way up there. Oh, that looks terrible. Let's try again. Let's go all the way up, over, and then bring it down. Okay, that's good enough for government work, right? No, I'm just kidding. All right, so our function is behind us here. We don't really see it, but we're looking at these 4 rectangles. We're going to calculate the area of each one of them. So let's kind of organize our work over here. Remember that area is delta x times f at that x star subscript. So our delta x we said was 1/2. We're going to multiply it by the function value here. So we have 1/2 times 0, 1/2 times 1/4, 1/2 times 1, and 1/2 times 9/4. So we've got 0, 1/8, 1/2, and then 9/8. And let's convert 1/2 into a fraction with the same denominator as our other fractions. So that would look like 4/8. So we've got 1 plus 4 plus 9, which adds up to 14 over 8. And the decimal approximation of that is about 1.75. Some squared units. So we don't know what these units are if we're talking about feet or inches or yards or meters. So we could just say 1.75 units squared if we wanted to. So that's our left approximation. We're going to repeat this process, but instead of using the left endpoints to create our function height, we're going to use these function values as the right endpoints. So we're going to draw our rectangles this way, and then we will use 2. So let's take a scroll down and actually I'm going to erase this and kind of start fresh. All right, we're essentially doing the same problem, but this time we're going to approach it using the right endpoint. And because we're still working with the same function and we're still working with the same interval and the same number of subintervals, a lot of this gets to be recycled. For example, our delta x is still going to be 1/2, and our subdivisions on our interval 0 to 2 look the same, but something that will change is how we call x1, x2, x3, x4. Because we're looking at the right endpoints of our interval, we're going to skip 0. This is part of the interval that we're looking at, but it's a left endpoint, so we'll leave that off. For this first interval from 0 to 1/2, our x1 is the 1/2 value. Our x2 is 1, our x3 is 3/2, and our x4 is 2. So this time we will include the 2, the farthest right side of the interval, but we're not including the 0, so it kind of swapped off from the left endpoint picture. We still want to evaluate each one of these x's in our function. So when we plug x sub 1 into our function, that looks like 1/2 squared, which is 1/4. x2, that's 1 squared, or 1. x3, that's 3/2 squared, or 9/4. And then x4, or 2 squared, which is 4. And maybe you notice that a few of these numbers are recycled. And we can draw our rectangles now that we have the heights for them. So this time, for this first interval, we don't have a rectangle 0 height. We have a rectangle with height of 1/4. For the next interval, we have a rectangle height of 1. Next interval, we have that really tall rectangle, height of 9/4. And then we're going to have one more even taller rectangle. It's going to actually go above the page. That one has a height of 4. So our picture has changed quite a bit, only because we're using the right endpoint. The function is the same. It's just the point that we're plugging into our function to calculate the height of our rectangles. All right, now we can calculate the area of each one of those rectangles. So we're just going to copy that function value into our products over here. So 1/2 times 1/4, 1/2 times 1, 1/2 times 9/4, and 1/2 times 4. We'll multiply all of these out and then add them up. If we type all of these into our calculator, we can find that the sum of this area is about 3.75. Now this is a little bit interesting. We looked at the area under the curve, and just for some perspective, let's think about the function x squared looks like this. And we specifically looked on the x-axis from 0 to about 2. And if we were talking about the area under this curve, then we're talking about this shaded region. And we found two approximation. Using the left endpoint, we found about 1.75. And for the right endpoint, we found about 3.75. So drastically different values. And that's why we call them approximations. But remember, we're only using 4 rectangles here. If we were to increase the number of rectangles, the 2 different approximations that we have would get closer and closer together. They'd get more and more accurate. And if we were to let n go all the way out to infinity, then we would get the exact area underneath that curve.